And this is based on some recent joint work with Amlan Bernati, who's currently walking on. Yeah, you can find this paper on arXiv if you just look up. You can find this paper on arXiv. Yeah. So what's the what's kind of the setting? So the setting of this paper is, or the setting of this talk is, and the perspective is coming from conformal dynamics. So I guess the notion of conformal dynamics should be hopefully relatively familiar, but just to sort of make things clear, here's a approximate definition of what I'm talking about. So we have a function. A function is which has differentiable with some polar continuous derivative. It's conformal if it's locally angle preserving, or locally it looks like a similarity map. But the point is that the similarity map that it locally looks like can vary depending on the point. And because we're sort of interested in fractal geometry, or I guess the perspective is this fractal geometric perspective, somehow the second assumption is also very natural, that the map is uniformly expanding, which just means that the derivative is sort of exponentially growing everywhere uniformly in the entire space. And I guess classic examples of the simplest examples of a conformal map or conformal dynamics is, like, for example, the times n map on the torus, multiplication by 3 mod 1, for instance. All right. So if you have a set which is conformally invariant, so if I have a conformal and uniformly expanding map F on some reasonable space, if I have a compact invariant set, so that is compact and is invariant on its map, then it's a result which is sort of in a slightly special case due to Falconer, and then independently proved by Pereira and then Gutierrez-Perez in 1997, is that invariance in its own right is enough to guarantee regularity of the set. So this invariant set actually has to have equal Hausdorff dimension and upper box dimension. So these three notions of dimension, Hausdorff dimension, lower box dimension, upper box dimension, they all have to be the same. So in some sense, the set is very homogeneous in space and also very homogeneous between different scales. I think everyone recalls the definitions of these dimensions. So one thing that I want to mention here is that the notion of conformality is very essential. That if you drop this conformal assumption, then this type of theorem just completely fails. So, for instance, this is already from even preceding these results, that the Hausdorff dimension and the box dimension of the attractor can differ. And then it's a recent result of Natalia Jurga that actually the box dimension itself need not exist if we drop this assumption of conformality. We just replace it with some sort of like properly affine map, where there's more contraction in one direction or more expansion in one direction than the other. But I'm not going to talk about this anymore. I mean, this is very much a kind of a interesting area of research, but I want to focus on conformal dynamics. So I want to focus on the setting in which things are conformal and uniformly expanding. So if things are conformal and uniformly expanding, and I want to say something meaningful, I want to not already be covered under the setting. Well, this assumption of compactness is somehow the one that I would draw. All right. Yeah, so here I say non-compact. So what's the kind of type of map that I have in mind? So the type of map that I have in mind is, for instance, the Gauss map. So the Gauss map is a function f of x just 1 over x mod 1. So if you imagine we draw the function 1 over x, well, 1 over x kind of goes up, has a singularity at 0, and then we take mod 1. So we just kind of smash it down until it lands on the interval 0, 1. And it's countably branched. So there's one branch here, but then all the derivatives are increasing, and the closer we get to 0, there's infinitely many branches which get arbitrarily steep. And the Gauss map is quite old, and sort of one of the reasons why people have been interested in it is because of this connection with continued fraction expansions. If you take a number, you can represent the number using this continued fraction expansion, where we take digits a1, a2, a3, and these are natural numbers. Then the continued fraction. So it's like a base n expansion, except instead of the base n operation, we're expanding with respect to this continued fraction. So what do invariant sets for these dynamics look like? I call these canonical invariant sets. I don't know if canonical is a reasonable word here, but if we fix a subset of the natural numbers, any subset, hopefully not empty, and we look at the set of points where the continued fraction expansion, where all of the digits in the continued fraction expansion land in this set I, then this is going to be an invariant set. That somehow, when you apply the map, it's like shifting the continued fraction expansion. Of course, if some digit does not appear anywhere, and then you shift things, well, the same digit is not going to appear anywhere in the tail as well. So this is the kind of map that I have in mind. All right. And I guess more generally and maybe more familiarly, the perspective they actually take is that that the set lambda is actually the limit set or the attractor for a countable conformal iterative function system in RD. So here we have some countable finite, like either finite or countably infinite collection of maps in RD, and then the limit set is equal to is invariance. It satisfies the usual invariance relationship. And this is the framework introduced by Malden and Urbanski in 96. And then because somehow we care about things being vaguely dynamical, that also means that we care somehow about open set condition. And I'm going to assume some sort of condition which is basically the open set condition for the entire talk. And I'm not going to define it precisely, but just assume that there's some sort of separation. Basically, this means that this iterative function system is somehow arising naturally from a dynamical setting. So there are no overlaps. I'm not dealing with overlaps at all. All right. Right. So maybe here's a quick picture to kind of get some idea of what's going on inside these invariant sets. So the invariant set is defined. Let's suppose this is the interval 0, 1, and then we have a bunch of maps, which is taking the interval 0, 1 down to these subpieces, right? And there's somehow this is not drawn very well, but there's kind of infinitely many maps, perhaps at 0, right? So what can we say about the limit set? Well, the first thing is that it contains essentially undistorted rescaled copies of itself, right? Because of this invariance relationship, that inside each of these pieces, we again have the same copy of the set itself, but because of the conformality assumption, this copy is undistorted. So basically contains, morally speaking, undistorted copies of itself. But then another distinction that happens in the countable case as opposed to the finite case is that we also have this interference from these orbit sets, which is somehow the set of the set of endpoints. So let's suppose here we can take the set of fixed points and the left endpoint at every single interval. In the finite cases, there's finite sets, so some of this is boring. But in the infinite case, this set can be non-trivial. And also emphasize that this doesn't just appear at level 1. This actually appears at sort of all small scales. And once it appears here, that actually appears everywhere inside every map recursively as well. And for notation, so lambda is the limit set, and then f is this called the set of fixed points, or maybe the orbit set or a single point. So f is going to denote some sort of set like this for the rest of the talk. All right. All right. So and very quickly, let me just define a few more things to talk about dimensions. So as usual, sort of in dynamical setting, that the dimension of this limit that is somehow related to some sort of pressure expression. Here, the natural definition of pressure is we look at the logarithm of the sum of the derivatives. I mean, this is the norm is somehow the supremum over the derivatives of a given branch. We just ask how much is we contracting in each branch. Now let's just take the average over all branches. So because we're countably infinite, the pressure is not necessarily nicely behaved. I mean, it looks like this in the finite case, somehow differentiable, very, very pretty. But in the infinite case, crazy things can happen. It can be positive infinity and immediately jump down to some negative values. So the pressure doesn't have a 0 and such and such. But anyway, regardless of this, the following result was proven originally in 96 and also in 99, is that the Hausdorff dimension of this limit set, well, it's morally the 0 of the pressure, taking into account that, well, maybe the 0 might not exist, but somehow it's the 0 of the pressure. And then in contrast, the packing dimension actually does not necessarily need to equal the Hausdorff dimension. The packing dimension and the upper box dimension, well, these are the max of the Hausdorff dimension, but then we also have this extra interference coming from this orbit set, from this set F. Okay. Oh yeah, there's a T missing in the upstairs. Yeah, sorry. Yeah, this is a pretty funny function if it doesn't sound like. Anyway, right. Okay, so we have results. We have results from over 20 years ago, 25 years ago, about Hausdorff dimension and packing dimension or upper box dimension. So what I want to talk about in this talk is, well, I want to somehow address these 3 questions. So the first question that I want to think about is, well, does the box dimension exist? So upper box dimension and Hausdorff dimension can be different, but what about the lower box dimension, I guess? So if it doesn't exist, what can we say about the lower box dimension? Maybe the third question is, well, okay, so even if the box dimension does exist, can we at least somehow give a simple comparable formula? So can we give a formula for the lower box dimension, somehow depending on the Hausdorff dimension, depending on the lower box dimension, the set of fixed points, and the upper box dimension, the set of fixed points, or maybe some other stuff. We'll see. But maybe some. So what are some easy things that we could say? Well, okay, so following. So first of all, what's a lower bound for the lower box dimension level set? Well, the Hausdorff dimension is of course the lower bound, and the lower box dimension of the orbit set of fixed points is also a lower bound, just simply because it's a subset of the set. Well, the lower box dimension is also upper bounded by the upper box dimension, And then the upper box dimension is equal to this value, which is the max of the Hausdorff dimension, the upper box dimension of F. Again, this is just this is the result of Molten-Nordvansky from 99. So in particular, we actually just from these bounds, we get two mechanisms for the box dimension to exist for free. So the first mechanism is that the box dimension of the set of fixed points exists. So of course, if these two things are equal, the lower and upper bounds are the same, then we're actually just done. And then the second mechanism is that F is a very small set, or that the Hausdorff dimension dominates. The upper box dimension of F is smaller than H, in which case, of course, these also coincide, as you can see. So I want to talk about sort of the results in this project, and the first kind of result that we have is that somehow this is the only mechanism for the box dimension to exist. That either the Hausdorff dimension dominates, or the box dimension of the set of fixed points exists. But if one of these two things does not happen, then the box dimension of the limit set actually does not exist. The box dimension exists if and only if we have equality of these so-called trivial upper and lower bounds. And so already this kind of gives a sort of a relative, this gives a complete picture of the existence of box dimension. But we can say more. So actually, we can give sharp bounds in terms of these quantities. So we have the Hausdorff dimension here with the lower box dimension, with the upper box dimension, and then D is just the ambient dimension. I mean, somehow our maps are nerdy. So if the upper box dimension of the set of functions is bigger than H, I mean, otherwise there's going to be some sort of degeneracy in this formula. But then then case one exists. So if this isn't satisfied, just look at one. So the lower bound is sort of the same trivial lower bound that we saw before. But it turns out that actually there's a better improved upper bound. The improved upper bound, just by taking the upper box dimension, actually isn't optimal. That it's actually strictly larger than this one, which is some kind of horrifying looking formula in terms of all of these quantities. But then perhaps the most interesting thing, or at least the most interesting thing to me, is the following: that actually this is sharp in a strong sense. It's sharp in the sense that any configuration which is permitted by 1 and 2 is possible. So no matter what value of the lower box dimension between these three things, so given that I've fixed this value, this value, this value, this value, and this value lying between these two bounds, I can always find a system for which has precisely this configuration. So any configuration permitted by 1 and 2 is possible. So this is sharp in the most general possible sense. So in particular, the lower box dimension is not a function of the Hausdorff dimension, the lower box dimension, the upper box dimension, and at the ambient. So actually, we need to take into account more information about the underlying set in order to actually understand what the lower box dimension is. All right. So I guess for the remaining 5 to 7 minutes, I want to talk a bit more about what's the intuition for the result? Where is this coming from? Where are these bounds coming from? Like how can you hope for something like this to be? Oh yeah, so I just mentioned this quickly. Okay, of course, that sure you can get restricted digit sets for continued fractions where the box dimension does not exist. I'm very curious if this has been written down before. It was something surprising to me that no one's ever done this, but I guess reasonable. Anyway, so there are restricted digit sets for continued fractions for which the box dimension exists, and of course, just emphasize again that non-compactness is essential. All right. Okay. So actually, this result, these three things, these things actually follow from a single result, almost as a black box. Well, black box plus 1. And the single result is as one. So okay, so in general, let's suppose that we're given a bounded set. Okay, well, we can define this number. Let's call it S sub e of r. Well, this is like the box dimension at scale r. Of course, the upper box dimension is the lim sup of this quantity, and the lower box dimension is the lim inf. But this is the best guess. If you had to guess what the box dimension scale r is, this is somehow your most reasonable guess. And then, okay, so what's this function saying? So this is saying that the box dimension estimate for the limit set at scale r, well, asymptotically, it looks like this function psi of r. And this function psi of r is this optimization which takes into account this. So this is the box dimension estimate for f. This is the convex combination of that and the Hausdorff dimension. And then for each scale r, I optimize over all possible values of theta. And then this gives me what so actually this theorem says that here is a very precise asymptotic formula for the box dimension estimate of the limit set at scale r. In terms of what sort of data, well, we need the full scaling information about the set of fixed points, and then we also need the Hausdorff dimension. And then these two things are enough. So somehow this is encoding more information than just the lower and upper box dimensions of the set of fixed points, because that's the lim inf and lim sup. So we actually need all of the intermediate scaling behavior as well, in some sense. All right. Okay. So what is this is kind of crazy. If you just look at this, you're like, this is like kind of like what sort of intuition do you have for what's going on? So I want to say something about what does this formula mean at a heuristic level. So let's recall the structural result from earlier, right? So what are the two properties of a self-conformal set? Well, the first property is that, well, the limit set contains undiscarded rescaled copies of itself. And the second property is that the limit set contains the orbit set F. So these were sort of these two structural properties for countable systems. Well, okay, kind of reversing the order. So two somehow implies something relatively uninteresting or interesting depending on your perspective. Is that, well, of course, the covering numbers of the limit set have to be lower bounded by the covering numbers of the set of fixed points, just by being a subset. And the second one is slightly more exciting, because it contains an undistorted rescaled copy of itself kind of everywhere inside every single cylinder set. Well, that means that actually the limit set is h-dimensional between all pairs of scales and most locations. So I mean, I put this in quotes because all of these are sort of approximate in some sense, that it's not everywhere. This is very close to saying that the lower dimension of the set is equal to the Hausdorff of the set. This is not precisely true, but it's somehow close enough to being true that it's not a problem. So there are these two facts. So whatever this number is, whatever the covering number of the limit set has to be, well, it has to satisfy these two properties. And somehow it has to be lower bounded by this thing, and also it has to satisfy the second growth rate condition. And actually, what this theorem says is that, yeah. So let's just say here that the condition 2 is a growth rate condition. It says that somehow this number cannot grow too slowly. It always needs to grow. It always needs to at least be growing like a set which looks like it has conflict. And then, so a restatement of the other theorem is that the covering number of limits is as small as possible while satisfying 1 and 2. So basically, these are the only two obstructions for why the covering number can be larger than you expect. The first obstruction is that it has to contain the set of fixed points, and the second obstruction is that it has to be at least image-dimensional. But these are the only two things that otherwise the covering number is as small as possible. So that's where that formula is actually coming from. And then the sort of the version of before is just kind of a very precisely written version of this fact. All right. So here's sort of a picture that I think is kind of helps. So in Dash we have this sort of covering number of the set of fixed points, and then the solid line is the covering number is this kind of the covering numbers of a limit set. So here the kind of the box dimension does not exist. So this number is kind of oscillating. That sometimes it's fine, but sometimes the covering number of the underlying set is actually decaying too fast. It's decaying faster than is permitted by the Hausdorff method. And then here, the covering number of the limit set has to decay slower, but eventually it catches up, and then it sort of follows, and then so this is kind of the picture that kind of corresponds to that theorem. That some places it decays too fast, and then when it decays too fast, these two numbers are going to be different. All right. Do I have time to do this? I don't think I have time to do this. I'm just going to say there are some ideas about how to prove the upper bound. Fine. Great. Thank you very much.